Thanks so much for the introduction. I'm really sad not to be there in person. I love visiting Santa Barbara, but I hope that if I come down, drive down in a couple of weeks, I'll still get to meet some of you. Okay, so I'm going to be talking about some work that we've been getting into in a kind of a tentative manner, I'd say, in my group over the last year and a half. I'm actually kind of amused that I'm giving a talk at an ML conference. I was one of those people that was skeptical about the whole thing to begin with, but I think it was the protein folding problem breakthroughs that came from ML that sort of pushed me over the edge. But anyway, so what I'm going to be talking about is applying ML to the gravity wave problem in the atmosphere. And I feel like this problem has been set up in a whole number of ways, but applied to slightly different problems, such as ocean eddies, convective parameterization clouds, and so on. And also some of the issues that we're having with coupling it to a GCM have already been described by Alistair on Monday, I think. So you've heard some of this before, but let's see how this goes. So let me set up the problem to begin with. Gravity waves or buoyancy waves are quite ubiquitous in the atmosphere, so they form all the time. They form whenever there's flow over mountains, orography, moist convection, geostrophic adjustments, unstable shear, eddy-eddy interactions. There's a whole spectrum of things that sets off gravity waves, and then they propagate both in the vertical and in the horizontal. And at some point, they go and they break somewhere else in the atmosphere, and they deposit momentum. And so they have an effect on the large-scale flow. So what I'm showing you here on the right is just some Hofmiller diagrams. This is at the equator. This is ECMWF winds. So if you take out the mean, you see these tiny little fluctuations on the time scale of days. And they're tiny both in terms of being small in length as well as high frequency. So despite the fact that these oscillations, these fluctuations are of the order of, let's say, 10 to the 2 to 10 to the 5 meters, they actually do have a substantial impact on things like the jet stream and the polar vortex and these planetary scale phenomena that we all know and love. So they play a substantial role in the momentum budget of the jet, and then they also play a leading order role above that in the middle atmosphere and above that. They also play a role in things like polar stratospheric cloud formation and tropical cirrus clouds and so on, which are actually a pretty big source of uncertainty in climate models. So gravity waves are a really nice example of the multi-scale nature of fluid dynamics. And I don't know about you guys, but I was kind of thrilled to see the physics Nobel citation this year, where they had the sentence about the discovery of the interplay of fluctuations from atomic to planetary scales. And there was also a sentence about how these systems are complex and they have rich emergent behavior and they're difficult to understand. So I'm kind of excited that we're all in this difficult to understand field because it's difficult to understand, I guess. But anyway, so coming back to the problem, these waves, these buoyancy waves are forced pretty much everywhere in the atmosphere. They're tiny, but they have a role in the observed large-scale flow. And they're a source of uncertainty in climate prediction. We've talked about parameterization in a whole number of ways already in this conference, but a parameterization is basically just a black box. It's some set of fudge factors that tells you what the effect of these small scale processes are on the observed on flow that the model can actually resolve. And gravity wave parameterizations in climate models are actually rather primitive and have remained so for the last couple of decades, I'd say. Crucially, they are all single column in all climate models as of now. So the waves are not allowed to propagate in the horizontal. They are definitely not observationally validated because this whole spectrum of waves is difficult to systematically observe, and also they're not resolved. So that's a problem. And just to make things even more complicated, they depend on under-resolved sources such as convection, which is itself parameterized. So just to give you an example of just how bad the situation is, this is a paper from 2010, and this is from the Canadian model. I don't mean to pick on them. Any other model would be equivalently bad, I'm sure. So what we're looking at here on the left and in the center is two equally defensible gravity wave parameterizations. So this is the CO2 response. So they took the model, put in two different GWPs, both of which are equivalently defensible, and then they double CO2. So this is the sea level pressure response to that. And this right column is the difference between the two. So as you can see, even in something as basic as SLP, there's huge differences both in the sign as well as the magnitude of the response. And I wouldn't expect this to be significantly different now in the CMIP 6. So clearly this is a problem. We can definitely do very much better than this. We can put in something that's very much more physical, I would imagine, as a gravity wave parameterization. And so we clearly need novel approaches, which we are attempting to throw at this problem. So we are attempting to bring together a big bunch of people to address this problem in a whole number of ways, including new observations, including using high resolution simulations, both global climate models that are run at very high resolution, but for short periods, say a few weeks, as well as models like WRF, which are not global, but then they're very high resolution in their domain, as well as we could call it ML or data informed methods or whatever you want to call it. But that was the thought, and this is what has resulted. So we recently got pretty generous funding from Schmidt Futures and put together this nice project, which we call Data Wave. It's not really an acronym, it's just a name, which kind of made sense to me. We deal with data and we deal with waves. So please come check us out at this website. I've listed all of our project partners at the bottom. So if you have students who are interested in doing a PhD or postdocing with us or just spending a few months in the summer, send them along. It seems like we're always looking for people. But having said that, I'm going to spend the rest of the talk talking about something that is pretty much in my group. And this just arose from a concatenation of circumstances. I found this great student who was an applied physics master student, but I think I've converted him now. He's a PhD student at UW doing a PhD in climate. But so I found him, and then I was also talking quite a bit with the professor in computer science at the time, about a year and a half ago. And so I thought, well, let me just get into ML like a tiny bit and see where it takes us. So just as a proof of concept, what we're trying to do here is emulate the gravity wave parameterization of Alexander and Dunkerton. So this is extensively used in a number of GCMs even now. And we're doing it in a model that is kind of in between a full GCM and a die-core. So it's one step on the hierarchy, I guess. And it's part of the GFTL FMS, which I have been playing with for, I think, 10 years now. So it should fit well into the GFTL framework. It's sort of an intermediate complexity model. It has interactive water vapor and a troposphere and a stratosphere and sources of gravity waves and so forth. And importantly, it has this Alexander and Dunkerton GWP, which mimics the time and space averaged effect of many discrete intermittent packets of gravity wave drag. So basically all it does is that it adds a forcing term to the momentum equations. And it's also single column, but then we've got to start somewhere. It was developed by Martin Euchre back at NYU 4 or 5 years ago at this point, and it's been used for a few things. It's more complicated than a die-core, and it's not quite a full GCM. So that's what that is. And here's our ANN architecture. I'll talk a little bit more in a couple of slides about different inputs that we tried to provide and see how it went. But to begin with, and this was basically put together by Jerry Kane, who's a professor in CS over on campus. So to begin with, what we did was we gave it everything we could think of to train on. So U, V, vertical wind, temperature, altitude, latitude, longitude, surface pressure. And we trained two different NNs. So one for the drag in the zonal direction and one in the Y direction. And this is again single column. So I'll just move on, I guess. And good news is that it seems to do really, really well. This version of, we call this NN WaveNet, and it seems to do a pretty good job. So what you're looking at here is the drag at 100 hectopascal, which is sort of the entrance to the middle atmosphere, and it's WaveNet on the left. Do you see my mouse? I'll just assume you do. So it's a WaveNet on the left, and on the right is the 8099 parameterization. The difference between the two is in the center. And the differences are really tiny. So the drag associated with the 8099 parameterization is captured really well. And one could put this in different terms. One could look at the R squared or the mean squared error or whatever. It does really, really well. I'll talk a little bit about its offline performance and then talk about its online performance. So here's the QBO. The QBO is thought to be driven primarily by these gravity waves, so getting it right is kind of important. And interestingly, it generalizes pretty well. So what we're looking at here is that WaveNet has been trained just at one phase of the QBO. And just based on that information, it seems to be able to go through the full phase of the QBO as well as initiate the next round of the QBO. So on top here is the 8099 and bottom is WaveNet. It seems to overestimate the drag associated with the QBO in these places that I've pointed out, but overall it seems to do all right. And it generalizes between different phases of the QBO, which we thought was interesting. We haven't gone, I guess, quite as far as Mike just was discussing. But then we also tried training WaveNet on different combinations of variables to see what exactly was important enough that made it into how important is what when it does this training. We also looked at Shapley values a little bit. But the takeaway from this slide basically is that WaveNet gets the drag right as long as you give it the zonal wind for the zonal drag and the V wind for the meridional drag. And the Shapley value analysis basically told us that the two things that are most important is the wind just above and below the level of interest, which kind of makes a little bit of sense if you think about the theory of how linear gravity waves propagate on a given mean flow. We understand that very well. So I think we might be going down this path a little bit going forward to try and sort of take apart what the NN is actually doing and what's important. And this might also help in terms of having it spend less time and slow down the model. Okay, so that's all offline. And what happens when we actually couple WaveNet with NEMA, which we've done. We've been struggling with it quite a bit, really. But I'll say something positive now and then say something negative later. So this version of WaveNet, this first version of WaveNet that we came up with, which is actually rather expensive, is stable for 200 years or so when it's run online with this version of NEMA. I also say that this version of NEMA actually has less variability than it should in terms of comparing with observations. It has fewer sudden warmings, it has less tropical variability and so on. But this version of NEMA with this version of WaveNet seems to be coupled and fine. Here's just showing you the QBO again. On top is the 8099. NEMA run with 8099. These are zonal mean zonal winds in the equatorial region, 5 south to 5 north, and 8099 on top, and at the bottom is WaveNet, NEMA run coupled to WaveNet. And the period of the QBO doesn't appear to be statistically significantly different between WaveNet and 8099, which is good. The amplitudes are also a little bit different, but we think this is acceptable. So WaveNet couples, is stable, it produces a QBO, and the model hasn't blown up yet. So that's a good sign. Another nice thing so far seems to be the WaveNet generalizes reasonably well to increase CO2. So this is a complicated multi-panel figure, but maybe I can just focus your attention on panel F and panel I down here, which is the difference between the CO2 response. So this is quadruple CO2. So this is the difference between the quadruple CO2 response if you use WaveNet versus if you use 8099 in NEMA. In both cases, it seems like the polar vortices become a little bit stronger. The metallurgy jets also seem to become a little bit stronger as also move forward, which is expected. There's some statistically significant differences between the CO2 response, but they're qualitatively similar, and nothing crazy happens. So it seems to generalize reasonably well, at least in this version of NEMA and this version of WaveNet. Okay, let's say one more thing about the QBO, which is that I don't think we really understand whether the QBO amplitude and period should increase or decrease under climate change, but at least in this version of NEMA again, under quadruple CO2, it seems like the period of the QBO goes down, both if you use the physics-driven, well, the 8099, and if you use WaveNet. The amplitude of the QBO, however, appears to go down a little bit with WaveNet. And we're looking into this a little bit. I don't know how much further we're going to go down this path, but at least it's coupled. It's generalizing reasonably well to different conditions, to conditions other than it was trained on, and it produces a QBO when it's coupled, which I think is kind of nice. So let me see. I don't know how I'm doing on time, but I'll just keep talking until you stop me.
We have 15 minutes to go, so plenty of time.
15 minutes. Oh, nice. Okay. So I thought I'd mention a few future directions, assuming we keep going down this ML route. Of course, we have a bunch of different ideas, but we could train on a true ray tracing scheme, which actually follows wave packets around the globe, both in the vertical and in the horizontal. We do intend to train on high resolution simulations, as I said, both global and regional simulations using WRF, or our friend Claudia Stefan in Germany is going to be running, I think, 2 kilometer by 2 kilometer global simulations, which are just a few weeks long, obviously. So any input that anyone has on training and NN on different sources of observations, I'd love to hear from you. We're also playing around with how much WaveNet slows down this GCM, and playing around with things like pruning, so setting some weights to 0, various ways of optimizing runtime. I'll also say here that with a very realistic version of NEMA, which has the right number of sudden warmings and the right tropical variability, we are not able to get WaveNet to couple and be stable. So it seems to blow up around year 8 every time. I haven't had the time to look into exactly why that could be, but we're thinking about it. And then I think we're intrigued by the possibility of moving to a GCM that is GPU friendly. NEMA is not. We're currently using Fortpy for the Fortran Python interface, and that seems to slow us down a little bit. WaveNet is also quite expensive. So at the moment, the coupling WaveNet with NEMA is slowing the model down by a factor of about 7, which really isn't great. So we've got some ways to go. And of course, our project partners on DataWave, including Pedram, who's in the audience, has all kinds of ideas about doing fancier things with ML. So we just have to see how it goes. I'm also kind of excited about training on observations, or at least bringing together some sort of observational constraint on what gravity waves are actually doing in the atmosphere, and this kind of an approach. So I'm just going to take a couple of minutes to do about that. And I don't know how many of you are familiar with Project Loon, but it's something that I heard about in a Spark meeting in New Zealand when I was a student. And I sort of kept my eye on it ever since then. And when I showed up at Stanford, I bothered everyone that I could think of until I got my hands on this data from Loon. So Loon basically came out of Google X, and they've been putting balloons into the upper atmosphere since 2014. And they shut down operations as of earlier this year, but there's a really nice, beautiful data set from 2014 to earlier in 2021, which is now all available on a data portal associated with Stanford. So please go download it if you want to. There's about 10,000 balloon tracks, and they just happen to measure latitude, longitude, height, temperature, and pressure. About every 60 seconds. I mean, some observations are a bit more frequent than that, but generally about every 60 seconds. And just as a comparison, scientific ballooning missions such as Stradiol have involved about like a dozen balloons. The data from those balloons is very much better in quality, of course, because they're scientific ballooning sessions, but they cost about of the order of, tens of millions of dollars per each of those campaigns, whereas the Loon data is free. So I thought that this was a rich, untapped source of observations of the atmosphere, of the upper atmosphere. So we've had one paper on this so far, which I encourage you to look up. It was just a first pass through the data. Here's showing you where the data is. It's pretty much global coverage, not quite. Just looking at this will tell you which countries will not have these balloons in their airspace, but it's reasonably global coverage, and it's also seasonally varying coverage, which is quite valuable. So we had this one paper out where we looked at spectra associated with gravity waves and how that changes through the seasons and through the latitudes and so on. Now, my postdoc Brian Green is working on a pretty sophisticated wavelet analysis of these gravity wave packets from Loon, where he's going to pull out packets of these waves in time frequency space using wavelets. And we're also collaborating with our French friends who have data from Stradiol and also Stradiol 2. I think a couple of them are actually in exotic locations right now launching balloons. So this is going to be a nice integrated data set of all balloon observations and momentum fluxes associated with them. So we should soon be able to tell you what the sources of these gravity waves are, whether it's orographic or something else, and where they are, how they vary through the seasons, and so on. So the hope is the data wave is going to bring together all of these different approaches, and that we will be able to come up with an observationally constrained picture of what gravity waves are doing in the observed atmosphere, has also come up with a physically meaningful, or at least a more physically meaningful way of representing their effects on the global circulation and its variability. So I'll stop. I'll leave you with this beautiful image of gravity waves. I know that I'm standing between you and a drink, probably. So thank you very much for your attention, and I'm very happy to take questions.
Thank you very much, Aditi. Questions? Any questions online? No? Aditi, I have to ask, I was feeling, I wanted to ask you this before, but we know gravity waves are ubiquitous in fluids, such as the atmosphere and the ocean, but the focus in the ocean has been on vertical buoyancy fluxes and not on momentum. And when we talk about generalization, I do wonder whether we should be taking advantage of your data sets to see what else we could be doing. And I was wondering, I'm not sure if the reverse is true, because we don't have the same sort of data that you have access to. But that is a generalization problem that's quite different to what you're currently thinking about, which is climate. So I was just wondering if there's anything to comment on that. You know who to talk to, right? About these things. But I was just wondering if that's another dimension in generalization that we haven't even talked about.
That's fascinating. I hadn't even thought of that. but I should have, given that my colleague Leif Thomas thinks a lot about.
Yeah.
Yeah.
Well, I mean, I'm just
I mean, they're
pointing
the
out
same
that we
equations,
parameterize
aren't they?
gravity waves too, but we do something different. We're going after something different. So,
Right.
yeah.
Well, I might come and bug you about that.
I have another generalization comment.
Mm-hmm.
I'm a little disturbed to see that you use latitude, longitude as an input.
Right.
Learning geography. And another kind of climate question is, if we wanted to do a past climate, the different geography,
Mm-hmm.
this obviously wouldn't work. So how do you get around that?
Right. Well, for what it's worth, latitude and longitude don't appear to add very much to our column averaged R squared. If you look back at this table, yeah, but I would think that it would be useful really, because if you know where the QBO is and you know where the polar vortex is, I would imagine that that would be useful information. Yeah, with past climates, I don't know. I'm sort of going back to Libby's, I don't know, neural network, I guess, which sort of kicks it to something else when it doesn't know. But yeah, it depends on how different the climate is.
Okay, Law.
Yeah, hey, Aditi.
Hi.
You, great talk. I think it's on, right? Yeah, it is. Yeah, I think maybe kind of following up on Alistair's comment.
Mm-hmm.
So if you're adding latitude and longitude, I mean, you can take latitude as the equivalent of your Coriolis parameter, right?
Sure.
Sine theta.
Mm-hmm.
So actually, you're just giving information about the fact that you're on a sphere. So I don't think
Right.
it's cheating, right? You're still giving.
Oh, I see.
That would still work in a paleo world because you're giving sine latitude, which is you're just on a sphere.
Absolutely. Yeah.
But I'm sorry to interrupt, but I felt like it might be learning the geography. I mean, maybe the input should be something like surface roughness and elevation or upstream elevation or something like that. That's what I was wondering, if it should be generalized in terms of parameters that we could expect to be able to measure from a paleoclimate too, rather than retraining. Yeah.
That's just convective, so it doesn't matter, right? So if they give latitude, it's just the same as just giving you an idea that, again, that you're on a rotating planet.
Sorry, I missed that comment.
No, I think Pedram was mentioning that it was convective parameterization you guys were doing, so continent was not. Yeah, for sure.
So this is a non-orographic gravity wave parameterization. If you were to include the orographic component, I think this would just include a phase speed zero source. It's rather a simple proof of concept.
Any other questions or comments? Okay, well, can we all thank Aditi again? And all of our speakers this afternoon.